So we will start with the first unit. So once again I repeat, the title of the paper is Nuclear and Particle Physics. In this you have 6 units, and the 6 units are general properties, nuclear model, radioactivity, nuclear reactions, detectors and accelerators. Lastly, particle physics, that's elementary particles. So we'll start with the first chapter. The unit 1. Unit 1 title is General Properties of Nucleus. So in this general properties, what are we studying is first the composition of nucleus. So what the nucleus consists of, what is there inside a nucleus. So we know that atomic structure, we know the atom is at the center and electrons are revolving around the nucleus. Now we go into the nucleus and then try to understand what is there inside, what is there inside a nucleus. So the facts constituent of nucleus and their intrinsic properties associated with the protons and neutrons, and then the other properties of nucleus, size of nucleus, mass of nucleus, charge of nucleus, density of nucleus. Most important is binding energy, average binding energy, how this average binding energy varies with mass number. Then the very important feature, that is average binding energy versus mass number curve, which we will be explaining. So binding energy is very important part in this. Other properties include angular momentum of nucleus, parity is a function, then magnetic moment of nucleus, electric moment of nucleus, and lastly the nuclear excited states. All these will be included, discussed in the first unit, that is general properties of nucleus. So you look at this slide, it is very interesting that we are just introducing you to the word, that is nucleus. So we know that as a student of physics, physics is study of nature, study of properties of matter, and all things around us are included in matter. And we also know that the matter is either solid, liquid or gas. And also we know that matter is made up of fundamental particles, so called atoms. If you multiply, so if you build up, as you build a wall with the bricks, keeping bricks one over the other, you build a wall. Similarly, any matter can be built up by grouping of atoms. So atom is the smallest particle of matter, and this atom is electrically neutral as a whole. If you look at the atom, it is electrically neutral and it is indivisible. So you cannot further divide into pieces. This was the statement by John Dalton. So you know that Dalton in the year 1802 made a important statement that atom is electrically neutral and it is indivisible. It is the smallest particle of matter which cannot be further divided. This concept, this idea of atom, that is indivisibility of atom, was continued till the first subatomic particle was discovered by J.J. Thomson in the year 1887. That the first subatomic piece of atom, first part of atom, is the electron. This electron was discovered by Sir J.J. Thomson in the year 1887. That is called subatomic particle inside the atom. So now till Dalton 1802, we know that atom cannot be divided. And in the year 1887, for the first time, atom was looked inside by Thomson and said that first subatomic particle is electron. So you know rest of the things about electron is negatively charged 1.6 into 10 raised to minus 19 coulomb, all that you know. So but first subatomic particle is electron. And further discussion of nuclear physics was started with the process of spontaneous radioactivity. Naturally, the Becquerel discovered that alpha, beta, gamma rays are emitted in the year 1886 almost simultaneously, that alpha particles are positively charged, beta particles are negatively charged, gamma rays are electromagnetic radiations. And you also know that the most important experiment for the nuclear physics is the Rutherford's experiment. So Rutherford's alpha scattering experiment, this is very important, which we will understand. And once we know the not the details of experiment, but the results of experiments are very important. If we know the results of experiment, and from the conclusion of Rutherford's alpha scattering experiment, the birth of nuclear physics started. Therefore, the word nucleus was for the first time used in the year 1911 by Rutherford, which is a conclusion or result of alpha scattering experiment. Meanwhile, neutron was another subatomic particle which was discovered in the year 1932 by James Chadwick. So if you look at the nucleus, it consists of positive protons and negative positive protons and neutral neutrons. So in all, a nucleus consists of protons, neutrons, neutrons together form a nucleus. So protons and neutrons are called building blocks of a nucleus. They are constituents of a nucleus. Protons and neutrons together form nucleus. Then how many protons are there inside nucleus is Z. Z is number of protons inside a nucleus, that is called atomic number. Z gives number of positive charges inside a nucleus. So if you look at 2, then 2 protons are there. So therefore Z is equal to 2. And A is mass number. So total number of protons plus neutrons. Total number of protons plus neutrons there, that is mass number A, and A minus Z, that is total mass minus number of protons, is neutron number. So number of neutrons is, if you remove Z from A minus Z is the total number of. So protons and neutrons form a nucleus. Number of protons is Z, that is called atomic number. Total number of nucleons, that is total protons plus neutrons, is mass number, and mass number minus protons is the neutron number. And in general, a nucleus is represented by X, so we read it as ZXA. So this Z gives positive charge, number of protons, A gives the mass number, A minus Z gives the number of protons inside a nucleus. Therefore, a nucleus is represented by ZXA. Proton is represented by P, its mass is 1.67, 2 into 10 to the power exponential, it is 10 raised to minus 27, energy is 938 MeV, so proton is 1 unit positive charge. So we'll see the details. Neutron is small n. Again, almost proton and neutron are of same mass, 1.67 E, that is 10 to the power minus 27. Energy 939, and there is no charge. So unit positive charge is 1.6 into 10 raised to minus 19 coulombs. So now we will be discussing the most important experiment, which is the birth of nuclear physics, or the starting point of nuclear physics is the Rutherford's alpha scattering experiments. So if you look at the left hand side of the slide, so there is a clear diagram illustration that we see that there is a atom with dotted lines, and the dark region at the center is the atomic nucleus, and there are positive charges on the nucleus and some neutrons are also there. So with such an atomic structure, continuously beams of alpha particles are incident on this atom. So continuously, see 1, 2, 3, 4, 5, 6. So these many number of alpha particles, alpha beam of alpha particles is incident on this atom. So if you see, many of the alpha particles, they went straight. This alpha particle went straight with small, very small deviation, no much change. So here also see that they are good. And few, say the second one, few, they were deflected by some 90 degrees. So you can see that this is, there is a deflection of 90 degrees. But 1 in 20,000, this is very, very important. 1 in 20,000 returned almost same path. So returning from same path means it is 180 degrees. 180 degrees scattering. 180 degrees scattering is returning the same path. So that has led to the conclusion of something. So I'll repeat. There is an atomic diagram in front of you. Nucleus is at the center with positive charges on the nucleus. Then beams of alpha particles are incident on this. Many of the alpha particles went straight, few scattered by 90 degrees, and 1 in 20,000. So if you incident 20,000 alpha particles, only one among 20,000 retraced the same path of incidence, that is 180 degree scattering, which is also known as large angle scattering. So let us see why all this happened. See, once again, results of alpha scattering, most of the alpha particles went straight without any change, few deviated through 90 degrees, and 1 in 20,000 suffered 180 degree large angle scattering. Why this is happening is, so at the center of the nucleus, Rutherford says, as if whole mass of the atom is concentrated at a single point. So rest of the thing is empty. Therefore, the electrons are going straight without any scattering. All the mass is concentrated at the center, which is highly condensed and it is positively charged. Therefore, the alpha particle, which is also positively charged, comes nearer to this, and because of Coulomb repulsion between alpha particle and nucleus, it is deflected by large angle scattering. Therefore, this part at the center of the atom, there is something which is very dense, as if whole mass of the atom is concentrated at a single point, and it is also positively charged. Therefore, the alpha particle, which is positively charged, is experiencing a large angle. Then Rutherford named this center of the atom as nucleus in the year 1911. So the nucleus, which was named by Rutherford in the year 1911 as a result of alpha scattering experiment. And when you look at the atom itself is very small. Atom is very small, which you cannot see directly. The atom dimension is 10 raised to minus 10 meters. So it is very small, 10 raised to minus 10 meters, very, very small. How about size of nucleus? How you can measure? So you cannot take screw gauge and measure the radius of nucleus, but we know that because nucleus is stable, nucleus is having a spherical shape. Shape of the nucleus is spherical, and we can estimate from the experiment mean radius of the nucleus, and it is found that 10 raised to minus 14 meters is the radius of nucleus, and radius of atom is 10 raised to minus 10. Therefore, atom is smallest, nucleus is still smallest. If you compare atom and nucleus, so nucleus is 10,000 times smaller than an atom. Nucleus is 10,000 times smaller than an atom, and such a small nuclear size, nuclear radius is measured in very small quantity, which is called Fermi. 1 Fermi is equal to 10 raised to minus 15 meters. Nuclear dimensions are measured. Nuclear dimensions are measured with a very small quantity called 1 Fermi, which is equal to 10 raised to minus 15 meter. And since we cannot directly derive expression for radius, where r is radius of nucleus, you can estimate it is approximately equal, not exactly equal, approximately equal to r naught a to the power 1 by 3. R is of the order of r naught a to the power of 1 by 3, where a is a mass number which gives total number of nucleons in a nucleus, that is proton and neutrons together are called as nucleons, parts of nucleus. So number of protons plus number of neutrons is a, and r naught is a constant, its value is 1.3 into 10 raised to minus 15 meter. So first property of nucleus is its size, because nucleus is very small and we cannot directly measure the radius of nucleus, so we can compare with that of an atom. So nucleus is stable, therefore it is spherical in shape, its radius is 10 raised to minus 14 meter, while that of atom is 10 raised to minus 10. So if we compare radius of atom and radius of nucleus, the nucleus is 10,000 times smaller than atom, and these small quantities are measured in a new unit, for that is 1 Fermi. That Fermi is equal to 10 raised to minus 15 meters, and the size of nucleus is estimated by a empirical relation. A relation is found out as a result of many experiments, and the result, where r is radius of nucleus, is of the order of r naught, a constant, and a to the power 1 by 3, where a is mass number. So using this relation, so you can determine radius of a nucleus. So example, so you know that 6 carbon 12 and 92 U238. So these are the two nuclide. 6 carbon is smaller, 92 U is bigger, because in carbon 12 only 6 protons are there, in uranium 92 protons are there, and in carbon 12 nucleons are there, protons plus neutrons, 6 protons, 6 neutrons. So here 92 protons, remaining 144 neutrons, so 238. So this is a heavy nucleus. So radius, how you can find out radius of 6 carbon 12 is, if you know only A, if you know this, you will be able to find the radius. So use the expression r equal to, this is r naught, which is 1.3 into 10 raised to minus 15 meter, A is 12 to the power 1 by 3, so it comes out to be 3 Fermi. 3 Fermi, that is 3 into 10 to the power minus 15 will be the radius of carbon 12. So if you compare with uranium nucleus, once again 92 U238, R is R naught A raised to 1 by 3, R is equal to R naught is same, where A is, instead of 12 it is 238 to the power 1 by 3, and it comes out to be 8.1. So this is 3 Fermi, uranium is 8 Fermi. So carbon nucleus is smaller, whereas uranium is bigger. So you can estimate the size by this expression r equal to r naught a raised to 1 by 3. The nuclear radius is estimated from scattering experiments of neutron by the nucleus. Second property is nuclear mass. This is very interesting, and some aspects you know about this also. That is nuclear mass what is nuclear mass? Because of what is there inside a nucleus. So what is there inside nucleus is number of protons and neutrons. So inside nucleus only protons and neutrons are there. So their mass is the nuclear mass. So in a nucleus there will be z number of protons and n number of neutrons. Z number of protons and n number of neutrons will be there. So together they will give the nuclear mass. So there, that is what we assume. Assumed mass is how many protons are there, their mass of one proton, mass of another proton, mass of third proton, mass of fourth proton inside nucleus, plus mass of one neutron, mass of second neutron, mass of third neutron in the nucleus. So if we add them, that is called assumed mass of nucleus. So we are trying to understand what is nuclear mass. So assumed mass is mp is mass of proton, z is number of protons. So how many? That is 2, 3, 4 is z, and mp is mass of one proton. Similarly, n is how many neutrons are there, and mn is the mass of one neutron. So total assumed mass is, if there are two protons, z is 2, mass of one proton 2 into mp. If there are two neutrons, n is 2 into mn. So this is assumed mass. So take one proton and take another neutron, take next proton, take next neutron. Their mass, if you go on adding each particle by particle, that is assumed mass. Whereas mass of the nucleus is A is equal to m plus n. There is one very important equation you should remember, that real mass of nucleus is less than assumed mass. This is the actual mass of nucleus is less than assumed mass. Actual mass or real mass is as a whole. If you take mass of a nucleus as a whole together, protons and neutrons, if you weigh, that is the real mass. And if you separately protons and neutrons and then add their masses, that is the assumed mass. So real mass is always less than assumed mass. So this difference, actually same number of protons and neutrons are there. So when you weigh all protons and neutrons together, their mass is less. When you separately weigh them and add their masses. So this difference between real mass and assumed mass is called mass defect. This is very important aspect. Mass defect is real mass of nucleus minus assumed mass. So difference between these two. So this is called mass defect, and it is represented by delta m. Represented by delta m. So delta m is small difference between the mass, that is assumed mass is z number of protons into their mass plus n number of neutrons into their mass minus real mass. Real mass is together. So you can visualize here. So if you take the mass of a nucleus together, protons and neutrons as a nucleus is less than when separately two protons, two neutrons are separately weighed, which is, that is, some mass is lost when keeping the nucleons together. So that is, we are calling it as mass defect. So I repeat, so second property of nucleus is mass of the nucleus. Nucleus is very small. It consists of only number of protons, only number of protons and neutrons inside a nucleus. Z is total number of protons, n is total number of neutrons in a nucleus. Assumed mass is Z number into mass of proton, n number of neutrons into mass of neutron. Total mass is mass of proton plus mass of neutron. Real mass is as a whole, nucleus as a whole is less than when you weigh them separately and add the masses of protons and neutrons. The real mass is less than assumed mass. The difference between real mass and assumed mass is mass defect. It is given by delta m. So it is given by a simple expression ZMP plus NMN is the assumed mass minus real mass is less. So this difference is mass defect. So you can also visualize that as a whole nucleus, it is 2 helium 4, as a whole 2 protons and 2 neutrons together, the weight is less. When separately, 1 proton, another proton, 1 neutron and another neutron. So as a whole, weight is less when same 2 protons, 2 neutrons when separately weighed. So it means that in keeping the nucleons of a nucleus, in keeping 2 protons and 2 neutrons, some mass is lost or some energy is required to keep the protons and neutrons together, and that is why when we bring all protons and neutrons together and weigh, their mass is less when separately we weigh them. So this is called the binding energy, so which we will be taking up. Maybe we will discuss and continue further discussion in the tomorrow's class, same time 11 a.m. we will be meeting. So today we have started with the basic basic idea of a nucleus, that is alpha scattering experiment. The result of alpha scattering experiment was the large angle scattering, so which shows that the positive charge is concentrated at a point, therefore alpha particle is deflected by large angle. This was named nucleus by Rutherford. Then the nucleus is very small, nucleus is stable, it is spherical in shape, its radius 10 raised to minus 14 meter, atom is 10 raised to minus 10, nucleus is much smaller, 10,000 times smaller than atom, its radius is measured in 1 Fermi, 10 raised to minus 15 meters, so R is R naught, A raised to 1 by 3. Nuclear mass, the assumed mass is Z number of protons plus N number of neutrons. The real mass is less than assumed mass. So difference between these two is mass defect. Delta M is equal to ZMP plus NMN minus real mass. And when we weigh them together, protons and neutrons mass is less when separately weighed. So this is mass defect. So it means some mass is lost in keeping the nucleons together, and which appears as binding energy, which we'll see in the next class, that is binding energy, nuclear density and nuclear binding energy curve. These properties we'll be studying in tomorrow's class.